Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be introducing the concept of chemical potential energy. Okay, we're revisiting our treatment of energy using bar charts and thinking about how it applies in chemical change, something that so far that we have ignored. Or kind of left till later. Well, that time is now. Now, do be mindful that this concept is quite hard, and I really want you to be careful in taking notes and following along and really trying to kind of keep track of what is going on. Okay, so to start with, we're going to introduce what we mean by some of these concepts and how it kind of relates to energy and chemical reactions, and then we'll go through some examples using bar charts. Okay, so here is where we're introducing our ECH chemical our energy account that we introduced to start with. Remember that we had ETH, which was thermal, so relating to the motion of the particles, and then we had EPH, which was phase, which related to the arrangement of the particles. And now we have ECH, which relates to the connections, also known as bonding, within particles. Okay, so phase was connections or / interactions between particles. Okay, interactions is probably one of the better words to use here to show how the particles were kind of, there was some interaction in energy terms between them. And so we're going to now be looking at the energy that's involved in the bonding or connections within a particle. Okay, so we're thinking about molecules here, okay, as opposed to talking about ionic compounds. All right, not exclusively, but that's generally sort of the idea that we're talking about. Okay, so one thing that we need to so it's the energy involved in breaking and making bonds within a particle, within a molecule. Or I put particle more generally just to kind of keep things general enough. Okay, so breaking and making bonds is what happens during chemical change, because we've talked about the fact that chemical change involves rearranging atoms, and when those atoms are connected together in an existing substance, you have to break them apart before you can put them back together in a new way. Think about like a Lego model. If you've got a Lego pirate ship and you want to turn those bricks into a spaceship or a castle, you need to first pull those pieces apart, and before you can then reconnect them in a new way. You still have all the pieces at the beginning and at the end, but because of the rearrangement process, you needed to break them apart to start with. And that's not an easy thing to do. In Lego terms, that takes energy, okay, because they don't just kind of fall apart, they're designed to stay together. And in chemistry terms, it's the same, that energy is involved in separating substances from one another, separating atoms from one another. And then when we reconnect them in a new way, that then energy is released as it relaxes back down. Okay, or kind of becomes more stable. All right, and so that there's a certain amount of energy that's involved here. Okay, so a few other kind of key terms that I want to touch on. Okay, so that we talked about, we've talked about in the past, probably last year, this idea that chemical reactions can be either exothermic or endothermic, in terms of what you need to do or what happens to the energy during that process. Exothermic is where energy is released during the reaction, and then endothermic is where energy is required to start the reaction. Okay, so typically we might be thinking about heating, or we might be thinking about electricity. Sometimes we're thinking about it in terms of light. Okay, but those are probably the main two that we'd be thinking here. So energy is released, and we might just add during reaction. Okay, for clarity. All right, and so that gives us information about how much energy is stored in the connections within particles in these types of reactions. Okay, so first of all, I'm going to show you how conventional chemistry textbooks would show this process. Okay, so they have a diagram which has energy and probably time or extent of reaction, something generic on the bottom. Okay, and we are going to be able to kind of connect this back together because in the HSC that these are the sorts of diagrams that you would be expected to see. I'm going to show you that they don't tell the whole story. Okay, so what we're saying is that we start off with a certain amount, so this will be exothermic, and this will be endothermic. Okay, so we start off with a certain amount of energy that is stored in our reactants. Okay, so let's say we're starting off here. Okay, so this represents our reactants in each case. Sorry if the pen is not quite clear enough. Okay, so we start off with a certain amount of energy stored in the connections in the reactant particles. Okay, and then what we're saying is that for an exothermic reaction, that as the reaction goes on, that we actually give off excess energy. We actually have less energy stored in our products than we had in the reactants. Okay, so it goes, the stored energy goes down by a certain amount, and the difference there is given off to the surroundings. However, in an endothermic reaction where we had to put energy in to start the reaction, what we have is the opposite, that our products have a higher amount of stored energy. Okay, and the energy difference there is how much that we had to put in. You know, if we had to heat it more strongly or we had to put in electricity, then we're talking about a big difference. If we only had to put in a tiny little bit, then we're talking about a small difference. Now, the reality is that we don't just have kind of a step and it kind of goes down, because we know that these reactions need a little bit of energy to start them off. Even a burning reaction, combustion, which is exothermic, needs a match or needs a spark or something to start it off, and then it kind of goes from there. And so what we see there is that actually that we have a little energy hill to get over, and then it drops down to there. In both cases, we have an energy hill that we need to get over before we come down to our products. Okay, because we have to put energy in to be able to break all the atoms apart from each other. So what we would say is here is that all bonds broken. Okay, and also we would say that's the point over here. The highest point of the hill represents all the bonds being broken, all the Lego bricks pulled apart, and then we're starting to put them back together again in a more stable way that either releases a lot of energy, so that we have less than we started with, or releases a little bit of energy, so overall we had more stored than we started with. Okay, and the energy difference between the two things there is the net energy change. Okay, and we give that a name. Okay, so that the net energy change, we call it delta H. Okay, change is delta, and then the stored energy we represent as a letter H, which stands for the word enthalpy, which is basically just a chemistry word for stored energy, or energy stored in the connections within a particle, within particles. Okay, so we now then need to start to consider, right, well, how can we use energy bar charts to better represent what's going on here? Because then it's kind of like, okay, well, once we heat it up, you know, let's say we're our endothermic reaction. Once we heat it up, why does then the reaction happen? And then how does that translate into our understanding of energy accounts? Okay, and how can we then make sense of what's happening over here? Okay, stay tuned for the next video. We'll go through some of that in a little bit more detail. All right, thanks very much for watching. Bye for now.